Anyway, so Vlad is not using the blackboard, I assume, so he will be talking about adaptive population enrichment designs. Thank you.
Thank you, Holger, and thank you, organizers, for giving me the opportunity to talk with you about this adaptive population enrichment design. And you may ask why this is important, and that's the first part of my presentation. I will explain you what this enrichment strategies is and what population enrichment means. And I will illustrate that with an example, and then I will briefly cover the methodology of testing, but is very much of an overlap with Chris' presentation. He is using seamless phase 2-3 design to select a dose. I will be using the same methodology, but selecting a subpopulation. So it will be very easy for me to go through that methodology because he already presented. But the focus of my presentation is on the estimation after this type of test, and is very similar to what Nancy was mentioning, and then of course Alessandra was mentioning that that's also very important. Yes, we do all these sophisticated designs, adaptive designs, but what do we do at the end when we reject the null hypothesis? Yes, we prove something, but how do we estimate? Okay. So motivation for this enrichment strategies. By the way, in industry, FDA released in December 2012 guidance for the industry about enrichment strategies. So you can understand how important this became now recently. But the whole idea, the whole movement in the industry towards personalized medicine is by this fact that now is recognized that this aspects of one size fits all, when we develop a pill that will be applied for everybody, is not sustainable anymore. There is a recognition that diseases are heterogeneous, population of patients with disease is not homogeneous. And this movement into personalized medicine is possible today because of achievements in discovery, understanding the disease, having a lot of biomarkers, or all this genetic revolution is giving us some possibility of doing better than just one size fits all. And so from discovery we are developing now drugs which are not again one for all, but they are very targeted for the mechanism of the disease. And then of course naturally you believe that if you target that population, the drug will be better than for the remainder of the patients with that disease. So that's the trend. And so like graphically to explain that, there is of course a recognition that patients with a disease, they are not all the same, at least 4 subgroups you can imagine. Some can benefit from efficacy point of view, but they may also have some toxicity or adverse event. And of course the best will be that you are in this group, drug is not toxic and beneficial, but you don't want to be in that group, of course. And this is the trajectory of where we are today. We are in the empirical medicine status where we develop blockbuster drug targeted at the whole population in a sense, but that of course is coming with recognition that yes, that business model is not sustainable anymore, because on the one hand, the era of blockbusters is kind of fading out. We are not so lucky anymore, but also is recognition from payers, especially in Europe, here being in the UK, that now not only to show the drug works overall, but it should have evidence that it works for the given patient, because then the insurance will cover or not. And this number here, which is recognized today, that on average 50% of patients benefit from a drug which is prescribed, another 50% don't benefit, is a big problem. So of course we want to be here in personalized medicine, which is like delivering the right dose to the right patient at the right time, but we are probably operating now in this precision medicine space, which is recognized that we need to develop drugs focusing on subgroups, not for the whole population. Okay, so what are the potential benefits for this shift in the paradigm of drug development? Is the patient will receive more effective drug with fewer side effects and giving better outcomes. We will avoid the time and resources wasted trying unsuitable medicine, and of course accelerating the whole development and availability of new diagnostic medicines and treatment. will benefit patients, healthcare providers, and of course business. Key concept of adaptive population enrichment. So now I'm bringing in this framework adaptive. So the idea is that can we now think about bringing more efficiency in this type of development when we will rely on adaptive designs. And adaptive now is in a sense that you want to extend from the conventional single population type of adaptive design focus to recognition upfront at the planning stage that the population might be heterogeneous, that the treatment effect even on placebo might be different from subgroup 1, subgroup 2, subgroup 3 of patients, and the treatment effect itself might be different in subgroup 1, subgroup 2, subgroup 3. In the terminology of biomarkers, these are prognostic biomarkers and predictive biomarkers. I don't have time to go in details, but that is in a sense. So you have to take that in consideration at the planning stage. Second, at the interim stage, you can decide, because there are so many now dimensions and so many kind of unknowns, perhaps it's good to not plan at the beginning, relying on these assumptions and wait until the end and then see what happened, but plan perhaps at least one interim analysis where you check these assumptions. So this is where adaptive methodology comes in place. But of course, you don't need only just to select, to look for adaptation on the subsets, but you can bring other elements of adaptive stopping rules, sample size estimation, and so on and so forth. So that's the key concept. So let me illustrate this by an example. Perhaps many of you, and I don't know, Peter, if you will present about iSpy in your presentation, because I saw it, but this is now very well-known platform trial. It's called iSpy 2. It's a development of many drugs for several subsets of breast cancer patients. And I'm using this just as an illustration. That trial is ongoing. There are always 6 treatment arms and control, 6 drugs. And if a drug is promoted because it's found to be the best in a subgroup, then it's moving into phase 3, and another drug is coming back into the mix. So already for the last 2 years, 3 drugs have been promoted. They say that they moved into phase 3. And so, for example, in breast cancer, they are using today 3 biomarkers, HR, HER2, and mammaprint. And you can imagine each of them is plus minus. And so you have already 8 subgroups that you can look at or select the patients or subgroup the patients. And then they created so-called signatures. So let's, for example, HR positive are this type of patients, HR negative are this type of patients, and so on and so forth. So now assume now that one of the experimental drugs in this iSpy 2 is now graduated, this is how they call college terminology, is graduated in phase 3, and is graduated because it was found to be the best among 6 drugs on treating triple negative breast cancer patients. And if you look at this diagram, triple negatives are these patients here, which have this type of signature. And now for that sponsor, for that pharmaceutical company which has this drug, they have a dilemma. How to develop now this drug in phase 3? They can go and do phase 3 just in triple negative patients. But the market value, so we are talking money here, it's in the industry, market value is not so promising. It's only 34% of the breast cancer patients. Oh, sorry. Oh, so big. Okay, I pressed not what. So, of course, they can take another kind of approach. How about we go in HER2 negatives, which contains this triple negative, but also contains this one. This is 63%. But there is a risk. Now, what if, indeed, the drug doesn't work in these patients, but works only in this patient? So if you don't do any adaptation, you go to the end, and maybe the treatment effect will be diluted and you lose altogether. So adaptive enrichment design comes as a compromise. So what we start enrolling patients in HER2 negatives, but have a pre-planned interim analysis. At that time, we will make the decision. Do I continue just with triple negative or with the whole HER2 negative patients? So outcomes then, again from the pharmaceutical point of view, you can have 3 types of outcome. You can get out as a result, if you'll be successful with a broad label in HER2 negative, you may get out with restricted label if you will get only success in triple negative. Or there is this one which is also important, it's called enhanced label, and that sees now how to say, with the competition, I may have a drug which is proven to be efficacious in HER2 negative, but better in triple negative than other drug. So that is giving you an advantage on the market, and that is very important to be able to show that in your phase 3 study. So, for example, this result will be better than this result, than this result. Okay? So now when we create the design, we need to take this in consideration and make sure that we can clarify all this during the study. So schematically, this is how it looks. You start enrolling in the full population, but you do have upfront the subpopulation specified. Peter will probably present you something where the subgrouping is not yet known, and he will be in phase 2 study kind of framework. But here I assume that this is pre-specified. But then you have one interim analysis. At that interim analysis, you decide, do you stop for fertility or efficacy? If not, then you have to answer another question. Do you go from this point in full population, or do you go in the subpopulation? And please pay attention here. If I go with full population, I still have to pre-specify at that time. I'm going to just go and at the end prove only F, that full population, or I want to retain also that expanded because that depends on how do you pay penalty for multiplicity. So that's very important. Okay, so now let's say how we design this quickly. The primary endpoint in that study is so-called the pathologic complete response, PCR, at surgery, and I want to run a study now with power 90%, significance level 2.5%. Control rate, that's for the planning stage, I assume that is the same, 0.3, and treatment effect is 20% difference from there, so better by 30%. So if I do quickly some calculations, I can come up with like about 300 subjects if that is the case for 90% power, but there is a kind of variation. If it's a bit better, I can get with about 190. If it's a bit lower, then I need about 500. So that's the ballpark where I have to operate in the sample size. So I quickly go and do some calculation now. I need to find what is the proportion of triple negatives in this like HER2 negatives, and I can quickly calculate that it's 54%. Now I looked at predicted PCR in the control arm based on the results from I-SPY1, and I'm getting there that in triple negative is 0.34, in the complementary to triple negative is 0.23. So I already see that triple negative is prognostic, that's first, and I don't know if the treatment effect will be the same or not. That's what I want to investigate through simulations. So then I will create 21 simulation scenarios where I will vary treatment effect in triple negative from 0 to 0.3 by 0.05, and then treatment effect in the complementary 0, 0.1, and 0.2. And I propose a design which will be a total sample size of 300 patients. In the first part, I will enroll 150 subjects, and then I will use this inverse normal p-value combination methodology to combine the data from the first part and second part. And for multiplicity, I will use Bonferroni, but I can use Symes or other methods that Chris was telling us in the morning. And I'm using selection rule, which is so-called delta or epsilon selection rule, which means at the interim analysis, I will look at estimate in the full population and estimate in the subset that I'm targeting. And if the difference is smaller than 0.01 between them, I will go with the full population. If not, then I will go with the subpopulation. That's called the 0-1 selection rule. And here I have some plots for you. So let's say this is like effect in the triple negative is going from 0 to 0.3, and effect in the complementary is 0.23. This is exactly the same as placebo. So this is a graph about the power as a function of effect in the triple negatives when the drug doesn't work at all in the complementary. So you can see what you expect. The blue line is probability of being successful. and I can be successful either showing the drug works in the full population or maybe only in subpopulation or in both. What is red is the probability to reject the hypothesis related to triple negative. So that's probability that I will be successful. I will be showing that the drug is working in the subpopulation. And because drug doesn't work in the remainder, you can see that the whole power, if you like, is coming from the probability that I will reject just a subpopulation. Because this yellow one is showing the probability that I will be claiming success in full population. Okay? So the picture will change a bit if now I allow the effect in the complementary to be 10%. So not 0, not 20, but half of that, 50%. And then you can see here that something changed, right? So the probability of getting successful in the subset is smaller. The power is now coming from either in subset or in the full, because probability of getting in the full is going up. And is competing now at the interim analysis. Sometimes I will say go with the full population, sometimes I will say go with the subpopulation. That's the trade-off. And if I do even 0.43, now it works 20% in the complementary. You can see now that, of course, my chance of getting success in the subpopulation is much smaller, and the probability of being successful in the full population is coming up. But I am still below 0.8%, 80% power in the full population, even when drug works in both of them. You would expect in that case to be up to 90%. So what are the elements of adaptation I can bring into the mix? I can do sample size estimation, because I have to look at that interim analysis and see where I am, and depending where I am, I can decide to increase the sample size either in the subpopulation or in the full population, but just to get or to recover the power to 90%. And I do a modification now to the design. I will allow up to 3-fold sample size increase at the interim analysis for the second part. And then I will try, like was Frank explaining about conditional power. I look at the data, and depending what I decide based on observed, do I go with full population or subpopulation, I would like to have 90% power, conditional power for that. And then total sample size, of course, will now raise from 300 up to 600. But is it going to be 600, and how often it will be 600? So I can now the plot that I showed you for 43, you can see that the power is raised now. In the 0.2, it's about under 90%, and in 25, this one is going up to 90%, because so the sample size estimation was working depending what is going on, but at what cost? And if you look at this axis here, is average total sample size. So initially it was 300. Now I allow it to go up to 600, but on average, just was barely about 300. In this region, which I am interested in, was probably about 360, 370. So with an additional, on average, 60, 70 subjects, I recovered the power going from 80% back to 90% that I expected. Okay, so that is, I'm trying to illustrate how this works and how what kind of adaptation we can bring in this framework. Methodology is simple. For example, we have several sources of alpha type 1 error inflation, and we need to deal with each of them. So first of all, we have interim analysis. So we need to adjust for interim analysis in this framework. And of course, we do that through error spanning or boundary, whatever. Sample size reassessment, we have to deal through combination of p-value from first stage and second stage. And then selection from multiple subpopulation, that's another source of multiplicity, and you deal with it through a closed testing principle, exactly like Chris was explaining. So what is nice, this adaptive procedure strongly controls the pre-specified family-wise type 1 error, so-called analytically. So you don't need to run simulations to convince FDA or EMA or PMDA that you control type 1 error, because through the methodology that is proved. Okay, so illustration, I think that p-value, Chris was explaining through the combination, combining the z statistics, but then he said that that's equivalent through p-value. So just I'm trying to explain here graphically the proposal by Peter Bauer, which is going back 25 years. Last year we celebrated 25 years from his pioneering paper. So the idea was, imagine that you have a two-stage design, and at first stage you fix two numbers, alpha sub 1, alpha sub 0, and you get the p-value based on data from of the test for the null hypothesis from the first one. So you can build now stopping rule. If it's very, very small p-value, you can reject H0. If it's very, very large, you can accept H0. Otherwise, you can go to the second stage, and now you are free to redesign the second stage as you wish. So you have a freedom of redesigning second stage based on data from the first stage. And then you collect the data from the second stage, and you create a p-value P2. And then originally he did this Fisher product test. So if conditionally on P1, I look at P2 is uniformly 0, 1. And because it's conditionally uniformly 0, 1, unconditionally is also uniformly 0, 1. So I can very easily find the C alpha, which will control the type 1 error overall. So you can see here just getting out of the restriction of using sufficient statistics, we brought a lot of flexibility in order to design what should I do based on data from the first stage for the second stage. And this methodology can be applied in not only in just very simple, but it was proved very powerful and successful in other applications. And of course, one which I'm talking about is the same. So because the product, you can quickly write that this is the high square with 4 degrees of freedom, or you can use inverse normal combination function like Chris was explaining, because now each of these components is uniformly 0, 1, and then you have the usual framework of normal distributed random variables. Okay, test strategies. You can think about combining this test through Fisher combination test, like I mentioned, with inverse normal method. As intersection test, you can use for the like this intersection hypothesis, you can use Dunnett. Like Chris was mentioning, you can use Bonferroni, Schreber, Symes, hierarchical, whatever you want, because everything will work perfectly. Now, for closed testing procedure, let's say illustration here, if I have full hypothesis and two subsets, S1 and S2, in order to reject this hypothesis in a one-stage design, I need to reject all this hypothesis and all hypotheses which imply it. So that's the closed testing procedure. If I have now second stage and I selected S2, how do I combine? And the trick is you combine this way. So you just create all combination functions with all hypotheses using data from the second stage and data from the first stage, and that will control type 1 error. So there are possibility to select now the subset at the interim as you wish, because like I said, there is a freedom. How do you select at the interim analysis? So this is a list of potential selection rules that you can think about, but of course is not exhaustive. It's not only the case that I illustrated. You can think about different other type of configurations. Let's say when you have two biomarkers, S1 and S2, and they may be of this nature, they may be of that nature, or this nature, or tree. Methodology works for all of them. And that's the first part about tests. How about estimation? So now imagine you conducted one of this trial, and you finished, and now you're asking a question. What is the estimate of treatment effect in the subpopulation, let's say in my case triple negative, or in the full population, or maybe in not triple negative population? So we are talking about estimation after an adaptive design. Okay, so let's take a simple example. So I have now the full population is split in S1 and S2, and then I have theta 1 and theta 2 is the mean of the primary endpoint in S1 and S2. Okay, and then overall mean is the combination where lambda is the prevalence of subset S1 in the full population. Okay, so that's natural. Null hypothesis, then I can formulate, this is for full population, theta is smaller than 0, and H01 is theta 1 smaller than 0. So because I know that drug works better in triple negative, so I'm not so interested in other null hypotheses, but you can in principle think about that as well, that treatment is smaller than or equal to 0 in theta 2. So now I want an overall sample size of 90% power for given delta. So let's say for delta equal to 0.5, that is sensitive. For delta 0.5, sample size is about 84. Okay? So now I have the form. So I'm looking as an illustration a very simple selection procedure. At interim analysis, after n1 subjects, and in first group and n2 in the second group, I have subset S1 and subset S2. If the observed mean is greater than observed mean in the second one plus delta, I drop x2. So I don't take x2 in the second stage. Okay, if that is a very simple rule, then I can say at stage 2 now, the number of subjects at stage 2 will be random now, because I'm using all n1 plus n2, so it will be n1 plus n minus m if I selected the S1, otherwise it would be n1. So this is the sample size for at the end of the study. And then theta 1, of course, depending what I have, is a maximum likelihood estimator, and I think Alessandro was telling us that although we do have adaptation, maximum likelihood remains the same. So yes, remains the same, but it's different depending on what stopping rule I have. The same you can do for T2. So that's the number of subjects in the second subpopulation. And then, of course, getting the theta 1 and theta 2, I can create an estimator for the full population. So now focus on one case here. I am interested in estimating or calculating the bias of theta 1. So I can write this, there is this nice fundamental identity in sequential analysis, which is based on change of measure. Okay, so you can take any function which depends on stopping time and statistics at stopping time, and for each stopping time which is finite with probability 1, you can write this kind of a differentiation under the integral. Okay, so you get to this one. So I can use this object to calculate the bias and mean square error. So quick algebra, I can write this way, and I can, if I take g equal to 1, I'm getting the bias of my estimator is equal to the mean, not bias, the mean of the estimator is equal to the true plus this object. So in order to calculate the bias of the estimator, I need to know this function, because that's the bias. So it's the derivation of the expected value of the 1 over t, where t is the stopping time. So if I know the distribution of t, I can calculate you analytically the bias. Okay? And so because I know how the t is created, I need to just take the derivative of this function, which is a very nice function. And this is the bias then of the S1, the estimator of theta 1, and similarly I can do the bias of the S2 or theta 2, which is this one. You can quickly see here, this is density of normal distribution, that bias of the first one is negative always, because this number is always smaller than that, and the bias of the second one is always positive. So now I can contour the plot of bias of theta 1, and here is a good contour between theta 1 and theta 2, how it looks. If you want to look in 3 dimensions, this is how it looks. So the bias of the naive maximum likelihood estimator is probably smaller than minus going from up to almost 0.01. Okay, so now can I do more than that? Yes, you can work with the same fundamental identity, get the second moment, get the variance, and what is important to get to mean square error. And this is the function for mean square error, so I already know how to calculate this. I need to calculate the second derivative of 1 over t squared, and of course we can go through that, and this is the mean square error now of theta 1. So that is how our naive estimator is doing. The question is, can we correct for it? It has a bias, it has quite a significant mean square error. Can we do better? Can we correct it? And of course, going back in the 80s, John Whitehead wrote a paper about bias-adjusted estimators after sequential design. So let's use that idea. So his idea is simple. If I have a function for the bias, then let's create an estimator which is the naive estimator and correct it. If I know the function, I can correct it through this equation. And hopefully, now this resulting estimator will have a smaller bias, and you don't know what will be with mean square error. So there always will be a trade. You may reduce the bias, but the variability may be greater. And I was very surprised that I was applying then you can, in order to solve that equation, you can create a Newton-Raphson iterative process and all stuff. I just did it very simply, one step, Newton-Raphson. So it's like very nice adjustment to the MLE. And I did some simulations here, and here are some results for the bias and for mean square error. The first line is naive estimator, MLE, and the second one is the bias adjusted, if you like, maximum likelihood estimator. For different configurations of theta 1 and theta 2, you can see here that, yes, I'm reducing the bias of the MLE considerably, but is coming, surprisingly, not at a big increase, and almost not that a big increase, but is very comparable with naive estimator mean square error, because that is well known in the literature of estimation after sequential analysis. There are estimators which are unbiased, so you can build an unbiased estimator after a sequential design, but unfortunately, why nobody is using them is not using because they are very hard to compute, and the second one is that their variance is larger than even the mean square error of naive MLE. So now it's a trade-off between bias and variability of the estimator, and I think that this kind of results are showing that you achieve kind of both of them. You reduce the bias. You cannot get unbiased because it's just bias adjusted, but it is coming with a nice trade-off between bias and mean square error. Okay, so conclusion, naive maximum likelihood estimator in population enrichment design has a negative bias. Bias adjusted MLE considerably reduces this bias and has comparable MSE. And conclusion in general about this adaptive strategy is an attractive and general procedure for adaptive confirmatory designs that controls type 1 error rate. The rules for adaptation and stopping for futility do not need to be pre-specified. Of course, if you want to stop for efficacy, you need to pre-specify, because then you touch the type 1 error, but otherwise you can kind of have a freedom. You can make decisions how to select, not only like I showed the list, which was frequentist, but to please Peter Muller, you can use Bayesian selection rule if you want, because the theory will work anyway. But of course, in order to, back to what Alessandra was mentioning in her point about simulation, I think to be convinced that this works or not, unfortunately, we need to run a lot of simulation and compare and contrast what is the value added of one element of adaptation versus another, and so on. So the role of simulations becomes increasingly important. And I stop here. That's the end of my presentation. Here are some references.
So there's already one question.
I was wondering about the size of those biases. So would the bias with the naive estimation, would that actually influence a decision, or what was the size of, I didn't...
That's an artificial kind of example. Is 83 subjects, and I picked a very large treatment effect, and yes, you can look at those numbers. I think that don't look at them in absolute, look at that relative. So relatively, you reduce the one bias of MLE considerably. Of course, in absolute value, because we're 3 digits there is no big deal, you can say. But I think that for perhaps other numbers or other configurations, those numbers could be important.
Right. Vlad, if I understand it correctly, when to quantify the bias, you have to prefix the adaptation rule, otherwise you cannot quantify the bias.
Yes.
But as you said, for adaptive designs, you just suggest you have full flexibility. So I have my doubts that in real applications, you can really calculate unbiased estimate, because you don't know whether people would have stick to the predefined rule in all circumstances. And so I cannot see how this can be applied in real life.
Very good question. And I think that's a kind of confusion of this slide versus previous one. Yes, for controlling type 1 error, we know for a long time that that is possible. Type 1 error doesn't matter what you do. Yes, for the doing this adjusted, I need to know the rule in order to calculate that probability. That probability that I showed you is exactly for that rule. And of course, then you have to follow that rule in order to quantify it. Sorry that I made this claim here as a general claim, but it should be just for testing. That's true. For estimation, you have to pre-specify and follow the rule of how you will do the estimation. Otherwise, you cannot estimate the bias or mean square error.
So maybe this is an unfair question because you didn't really talk about this subject, but
Don't ask unfair questions.
well, I'm interested in knowing how you identify these covariates for which there's differential response.
Mm-hmm.
And I mean, in the old days, in biometry days, we would be looking for treatment by covariate interactions,
Mm-hmm.
but phase 2 trials never have enough power to have a significant interaction.
Yes.
So,
So this is new kind of direction. It's not about covariate coming up from I don't know where. This is the science behind the development of a drug. So when you develop the drug, you have to know the disease and you know what you are targeting in that disease. So this subgrouping is done either on scientific grounds, or you have a previous study. In this case, in SPY, iSPY was iSPY 1, and then iSPY 2. Now they are running iSPY 3. So this is how the knowledge about this subgrouping, about where do you believe the drug will be predictive, prognostic, is based on this experience. It's not just coming males versus female, I don't know what, and let's put it in the design. So it's more scientifically driven subsetting of the population.
you wonder why they're so concerned with efficiency if they're within these trials, if they're willing to have a 1, a 2, a 3, and presumably there'll be a 4 and a 5 later on.
Drugs or subgroups?
Oh, trials.
Trials.
Talking about trials.
Oh, no, iSPY goal is completely different. iSPY goal is recognition that the multitude of diseases is so big that you as a developer cannot afford to test your drug in all of them. So the companies are coming together in this consortium where they say, instead of me trying all of them, I will participate in a race and I will use the same kind of infrastructure, but my drug will compete with 5 other drugs, and as you go in the trial, that design is picking who is the winner for a given subset, and is giving you that information, only that information, because of confidentiality. And as soon as you are found to be the leader, and there is the definition of that, that sponsor is getting that drug from the competition, and they go and do phase 3 study. That's exactly what I was trying to explain, how this can be applied. And you can imagine why this is better, because you are not just controlling versus placebo, you have a chance of controlling yourself with other competing drugs. And if you are, it's much easier to find a winner versus finding a drug which is better than placebo.
Okay, there's another question, last row.
I'm wondering, when you find an effect in what you call the full population, which in your example might actually be 2 subpopulations. So let's think of the full population. There's subpopulation 1 and 2. When you go to the regulator for approval, you'll have said, we set up this study and we really think the drug will definitely work for population 1, and it may even work for population 2 as well.
Mm-hmm.
And then you've got your results and you've done a test on the pooled data saying, yes, there is a combined effect. But actually, if you look more closely, you see that that's due to a big theta hat for your population 1, and maybe a very slightly positive theta hat, but not very significant, for population 2. Are they actually going to approve that drug for the full population?
Yes, that's a very good question, and it's back to the subgrouping and looking after the result of the study in subgroups. I think that what FDA is saying in their regulatory guidance in their presentation, that yes, definitely they will look what is the drug doing in the complementary of S1, in my case S2. And they didn't put rules, but of course they are talking if the treatment effect in the S2 will be in the same direction, not in opposite direction. They call quantitative interaction versus qualitative interaction. They will approve the drug in the full population.
If the p-value is below a half.
Yes, yes, yes.
That's very nice of them.
Yes, that's very nice of them, because in principle that is what we are doing anyway. Because what the numbers which I showed you is across all therapeutical area and is an average 50%. There are therapeutical area, let's say psychiatry, where it's shown that only 30% of patients benefited from the drug. So it's not a perfect solution, is sold as a better solution than what we are doing today.
Well, which is good, because they want to encourage more focused
Yep.
work, but at the same time, if you're doing that, you put people off.
Okay.
No more questions? Okay, then let's thank the speaker again. Thank
Okay.
you.